everyone, I'm Monica, and in this presentation I'm going to talk about the paradigm shift with the ultrathin and flexible silicon chips, the future of semiconductor technology. In this presentation, we'll see why we need these ultrathin flexible silicon chips, such as how they can make our lives easier, then how they are produced using the wafer bag thinning process and chip film process, and what are the various applications of these flexible silicon chips, such as printed and invisible electronics. Just imagine, you need to catch an early morning flight. As you painstakingly get up early, I certainly do, head for the shower, still groggy, a tiny flexible chip in yesterday's clothes remind you that they need to be washed. And not just that, some appliances will be automatically switched into the standby mode when you leave the house through the sensors in the carpet and wallpaper. When you get to the airport, your smart ticket guides you to the nearest exit, and your smart passport and a retinal sensor gives you immediate clearance. Wouldn't that be great? Such seamless integration of computing into everyday life isn't here yet, but it's not very far from becoming ubiquity. Radio frequency identification tags, known as RFID tags, are used to track goods and even pets and people. Flexible sensors in bendable displays are on the way for e-readers. Animated color displays are even printed on washable materials. Nowadays, these flexible products can be mass-produced and can even be printed to create large displays. We can also print rollable keyboards and molded car antennas. Currently, silicon chips are built on wafers which are 100 micrometers thick. If we go near 50 micrometers, the chip fractures under its own weight. But below 50 micrometers, an interesting thing happens. The chips become flexible and more stable. On further reducing the thickness to about 10 micrometers, the chips even become transparent. This opens up a huge window of applications such as those involving bendable surfaces, windows, and car shields. And here's the icing on the cake. Thinness also enhances stackability, which is required for fabrication of three-dimensional integrated circuits. You must be wondering, why do we need to make these chips thinner and thinner? Well, there are various advantages for doing that. First and foremost is better packaging density. The smaller and thinner the chips, the more number of chips can be packaged onto a single unit. Also, as we have seen earlier, thinness also makes the chips more flexible and more reliable. If the chips are thin, we can create various stacks of these chips for three-dimensional circuits. And lastly, thinner chips also provide better yields. It's a win-win scenario. The ultra-thin chips which are processed nowadays are primarily made from non-silicon organic and inorganic semiconductors, including polymers. But they don't perform as well as the conventional silicon chips. Silicon is an ideal semiconductor for such flexibility. Silicon's ordered structure allows for faster switches. Now, we will see how we can make these chips thinner. The most straightforward way is to make a conventional silicon chip and grind away the base. This can be done after the circuits are drawn on wafers and before they are diced into chips. Another way is to build a thin film of silicon on a layer of oxide which lies on a thick silicon substrate. These are called silicon on insulator wafers. The silicon is then removed selectively and uniformly. But both these processes have their drawbacks. Grinding and dicing introduce crystalline defects and cracks at the edges of the wafer. Also, both approaches need handle substrates to provide mechanical stiffness and stability. The device is bonded and then debonded to these handle substrates. And the separation of these chips from the handle substrates by wet or dry edge removal appears to be impractical because of high aspect ratio of the etching path underneath the chips. At the Institute for Microelectronics, Stuttgart, Germany, a new technology is being developed under the trade name chip film. The chip film technology features an additive approach in defining the thickness of a thin chip. It builds chips on slits and then snaps them off. Let's go through this process step by step. First, a porous layer is etched onto the top micrometer of a silicon wafer. Next, below this top layer, a 200 nanometer layer is etched with coarser pores. This is followed by sintering of the wafer at high temperature, which means that the coarser pores close in into a cavity. It's kind of like a hall of pillars, with the pores being the pillars and the hall being the cavity. This produces a high quality smooth substrate. Next, the fabricators build a thin layer of crystalline silicon on the substrate which carries the electronic devices. Almost all the electronic devices are located on this top layer, and it is this top layer which is of utmost importance to us. Integrated circuits are now constructed on the top layer of the crystalline silicon using standard lithographic methods. Dry etching is usually preferred as it induces lesser crystal damage compared to wet etching. The next step is to etch trenches right through to the underlying cavity, leaving only anchors at the corners or regions, which results in the substrate perched on top of the pillars. This is done to keep the chips in a weak attachment to the substrate. Finally, the last step. A pick-and-place tool grabs the chip from above, snaps it off the pillars, and removes it from the wafer, and we have to ourselves an ultra-thin, flexible silicon chip. The chip film wafers are roughly 20 micrometers thick, which is sufficiently thick for leaving them unsupported, yet thin enough to be able to expose them to binding tests. In part A of this figure here, we can see the cross-sectional scanning electron microscope image of the chip film wafer after etching, sintering, and epitaxial growth. Here's the inset, and we can see the cavity left after sintering of the wafer. What is shown in part B is that after the chips are trenched along the sides, only anchors are left at the corners, so they are weakly attached to the substrate. In this third part, the chip is first picked by attaching, then cracked from the wafer, and finally placed in the required circuits. This is done with the help of an automatic pick-and-place tool. Now this here is a really interesting image. This is the actual wafer area from which some chips were broken off. The darker area in the middle shows where the chips were. In the insert, a conventional and a chip film die are shown in comparison, and as we can see, the chip film die is a lot more thinner than the conventional die. There are some specific issues in wafer chip processing and handling. As seen in the images, the wafer can fracture due to its own weight, and also the edges of the wafer can get clipped. Sometimes, crystalline defects are also introduced in the grinding and dicing in the chip film process. Even if we manage to get an ultra-thin wafer without any damage and defects, there are some other problems with these chips as well. First and foremost is the cost factor. They cost about 10 times as much as conventional wafers and require extra substrates during handling. On top of these difficulties, these techniques waste about 99% of the silicon wafer, as only the top layer is utilized for chips and the rest of the base is ground and diced away. Even though the chip film process makes chips as thin as 10 micrometers, it's not yet ready for large-scale production. After finishing, the prized flexibility of these ultra-thin chips make them hard to attach to a substrate. Also, bubbles can form between the substrate and the chip. If pressure is then applied to the chip, these bubbles can fracture and die. Now that we've seen the why and how part, let's go to what these chips can do part. Here are some target applications of the ultra-thin flexible chips based on their mechanical flexibility, ultra-thinness, chip form and adaptability, and 3D chip stacking. The mechanical flexibility and reliability of these ultra-thin chips is exploited in the security chips in passports or bills, high voltage driver chips in flexible displays, and radio frequency identification tags. Smart cards need thin chips for form factor reasons. Also, power dissipation in the package is improved if chips are thinned down. Back-illuminated CMOS imagers are feasible only at minimum chip thickness. These chips have carved a niche in the medical field as well. Miniaturized chips are used in video endoscopes and diagnostic pills. They're also used to form biomedical chips such as subretinal implants. They need to be extremely thin so that they can adapt to the shape of the retina. Their ultra thinness also allows them to make extremely efficient stacks required to form 3D integrated circuits. Wearable technology. Perhaps the most promising field of application of the flexible silicon chips is the wearable technology. As we can see in the figure, there are mainly two types of applications, apparel and devices. Apparel includes weavable, washable, foldable, and printed transparent chips which can blend in with our clothes. The other type, the evolutionary devices, are typically mobile phone peripherals or variants with new human interfaces or diagnostic devices. Many big companies such as Intel, Adidas, Google, Samsung, and some more are investing in this technology. The other most important field of application is the printed electronics. These printed electronics use standard or in some cases slightly modified printers such as those used for inkjet printing or laser printing. It is the inks used in these printed electronics where the innovation lies. These electronically functional inks are used to print working and purposeful devices such as thin film transistors. The inks are made from semiconducting organic carbon-based materials in a solution-based format, making it possible to deposit materials onto a surface using additive or printing techniques. Currently, there are two major applications of the printed electronics, the smart window and the e-paper. The e-paper looks and feels just like regular paper, but it does much more than that. It stores and displays information like the newspapers in Harry Potter movies with moving pictures in them. It's no longer a magic. The smart window is installed like a regular window. It has a thin transparent film on one side which allows user to control the amount of light and heat passing through. The best and my favorite application of these ultra-thin chips is the invisible electronics. Nowadays, it's possible to include electronic components to almost anything and everything with printed and transparent electronic components. It can be done by simply applying a plastic film on the surface as the see-through circuits and power supplies have already been printed onto it. Right now, we're at the beginning of this new world with modest initial victories such as rollable keyboards. It's largely made possible by screen printed flexible metal patterns. Animated printed posters with sound interactivity and other electronic features can already be seen at various locations throughout the world, such as the Tokyo subway. They have their power coming from capturing the low level of lighting available using printed OPV. They are unrolled and applied just like a regular poster. The latest on the market are apparel, bags, and parasols that can charge our phone. It's not very far when the ultra-thin flexible chips would become an inseparable part of our lives. Here are some references that I've taken aid of for preparing this presentation. With that, I'll end this presentation. I hope you liked it. Thank you.